Hello and welcome back. In this lesson, we are going to talk about scalar and vector quantities. At the end of the lesson, you should be able to define scalar quantities and vector quantities. You should be able to distinguish between scalar quantities and vector quantities, and you should be able to give examples of scalar and vector quantities. So let's get into it. In the previous class, we talked about fundamental and derived quantities. Yes, fundamental and derived quantities is one way to classify quantities. It is based on whether the quantity is dependent on other quantities or whether the quantity is independent of other quantities. Scalar and vector quantities is another way to classify quantities. Scalar quantities are physical quantities that have only magnitude. That is, scalar quantities do not have direction. They have only magnitude. For example, if I say that the thickness of a thick slab or of a glass slab is 4.12 millimeters, that's just it. The thickness is 4.12 millimeters. How thick it is 4.12 millimeters. I don't need to, it doesn't make any sense to say that the thickness is 4.12 millimeters to the left or the thickness is 4.12 millimeters to the right. Thickness is just thickness. The thickness is just 4.12 millimeters. So such a quantity like thickness is a scalar quantities or a scalar quantity. Some other examples of scalar quantities are mass. Mass tells us how heavy something is. For example, if I say I want to get 3 kilograms of chicken, right? It's just 3 kilograms of chicken. It's just 3 kilograms. It's something like 3 kilograms to the right or 3 kilograms to the left. Or a bag of rice is 50 kilograms. It's just 50 kilograms. It's not 50 kilograms to the right or 50 kilograms to the left. So mass is an example of a scalar quantity. Speed, distance, time, energy, density, volume, temperature, work area, and others are examples of scalar quantities. Now, apart from scalar quantities, what we also have is vector quantities, which are quantities that have both magnitude and directions. That is, while a scalar quantity has only magnitude without a direction, a vector quantity has both magnitude and direction. And an instance is, for example, if I say I walk 3 meters, okay, if I walk 3 meters, that is just a distance, it is a scalar, because I've only mentioned that the distance I walked is 3 meters, that's a scalar. But if I say that I walked 3 meters to the right, okay, by saying that I walked 3 meters to the right, that to the right is a direction. So what I've specified there is a vector quantity, because I've specified the magnitude, which is 3 meters, and I've also specified the direction, which is to the right. Okay, so vector quantities have magnitude as well as directions. So you represent vector quantities with a line. That line represents the magnitude, and an arrow to show the direction, as you are seeing in the picture here. The length of the line, how long the line is telling you the magnitude of the vector, and the direction the arrow is pointing to is telling us the direction of the vector quantity. Example of vector quantities are force. Force is an example of vector quantity because an example of force is push. When I say something, I push something. Push means I'm pushing it away. I'm pushing it away from myself. Okay, that's the direction. It means it is being pushed away from myself. And then I pull something, it means I'm pulling it towards myself. So that is, you understand? Push means pushing away. Pull means pull towards. So those are forces, and you see that they have direction involved in their meaning. So they are vector quantities. Electric field is another example of vector quantity. Angular momentum, magnetic moment, linear momentum, velocity, and acceleration are also examples of vector quantities. So can you look at the list of quantities here and identify which are vectors and which are scalars? Force, speed, electric field, angular momentum, magnetic moment, temperature, linear momentum, average velocity. Can you identify which of them are scalars and which of them are vectors? Okay, so I think you've had enough time. Let's answer it together, right? Force is clearly a vector quantity. It has, like I just said, it has direction. Speed is a scalar quantity. Speed is just how fast an object is moving. It does not define a direction. So it's electric field. Electric field involves direction because it has to do with the direction which a positive charge placed in the field will move. Okay, so electric field has direction involved. Angular momentum. Angular momentum. It has direction because the angular there even means that there's a direction involved. Magnetic moment is a vector quantity. Temperature is just degree of hotness or coldness. If it is 100 degrees Celsius, that means it is 100 degrees Celsius. It is not, there's no direction involved. Linear momentum is another vector quantity. In fact, momentum is a vector quantity, whether it is angular or linear. And average velocity is a vector quantity. So relative velocity is the time rate of change of relative position of one object with respect to another object. What does this mean? Let's say you are in a car and the car is traveling, okay? And then there's another car parked on the side of the road. You are traveling towards that car and the car is parked on the side of the road. They say there's another car which is approaching you. It is traveling towards you. Then a third car which is traveling in the same direction as you. That is, it is like traveling away from you. Now, if you continue driving in your own direction, in fact, you're actually going to meet with the car that is moving towards you first. Then you meet with the car that is parked on the side of the road. Then it's possible that you meet with the car that is traveling in the same direction as you. So that gives us a sense that your change in your position relative to those objects is actually different, because you are going to meet with the one moving towards you first before you meet with the one that is parked on the road, and then it's possible that you meet with the one that is traveling in the same direction as you, right? So the velocity of car A relative to car B is written as VAB. Please note that VAB is velocity of A relative to B. So since I'm using car as example here, so velocity of car A relative to car B is written as VAB, and it is equals to the velocity of car A minus velocity of car B. VAB is equals to VA minus VB. And if you state the statement as the velocity of car B relative to car A, that is velocity of B relative to A, that is VBA, and it is equals to velocity of B minus velocity of A. So you can see from there that VAB is equals to negative VBA, because VAB is just VA minus VB, while VBA is the reverse, VB minus VA. So VAB is negative VBA, and this means that the directions of both relative velocities are inversely related. Yes, because VAB is equal to VBA. VAB is VA minus VB. VBA is just the inverse, VB minus VA. So the relative velocities are inversely related. And if you take the magnitude or the modulus of VAB, is going to be the same thing as the magnitude of VBA, because that is just the magnitude sign here shows that you can ignore the sign, whether it's positive or negative, and the magnitude is just the same thing. Now let's talk about resultant velocity. Resultant velocity of an object is the sum of its individual vector velocities. So let's just talking about, you have an object and the object moves in one direction, then it changes its direction and moves in another direction, then it changes direction and moves in another direction. So the resultant of those three vector velocities, which I've just mentioned, that moved in the direction, then in the direction 2, and then in the direction 3, the resultant, the effective velocity of that object is going to be the sum of the individual vector velocities. The resultant velocity is noted as R, capital letter R, to represent resultant. And we can look at some common scenarios of the resultant velocities. First is if the object moves in the same direction. For example, if you are traveling at 2 meters per second northwards, and then you speed up, and you now travel at 5 meters per second still northward, right? It means you are still in the same direction, 2 meters per second northward, then you just sped up, and you're now moving at 5 meters per second, it's still northward. In that case, your resultant velocity is going to be the first one plus the second, the 2 plus the 5, because it's still in the same direction. So in the same direction, the resultant R is equals to A plus B. In opposite direction, if you were traveling northward at 2 meters per second, then you reverse and you now travel southward at 5 meters per second, the resultant is going to be 2 minus 5, and that will be negative 3. So for the resultant in opposite direction, you have to take the difference. So for opposite direction, the resultant R is equals to A minus B. What of perpendicular cases? You are traveling northward at, say, 3 meters per second, then you now switch to travel eastward. That is perpendicular. Northward, north is perpendicular to east. So you travel eastward at 4 meters per second. In such a case, the resultant is calculated as R is equals to the velocity in the y direction squared plus the velocity in the x direction squared, then you now take the square root of that. It is actually obtained from Pythagoras theorem. R squared is equals to ay squared plus bx squared. Then you take the square root of that. That's r is equals to square root of ay squared plus bx squared. And the direction of the resultant is going to be the tan inverse of the vertical component, which is ay, divided by the horizontal component, which is bx. So that is the case when they are perpendicular, when they are at 90 degrees. The resultant is going to be equal to the square root of the ay squared, which is the vertical component squared, plus the bx squared, which is the horizontal component squared. The direction is going to be tan inverse of the vertical ay divided by the horizontal bx. So what of the case whereby they are not perpendicular? Because perpendicular means that they are at 90 degrees to each other, right? What if you have a vector A and a vector B that are not perpendicular, rather they are inclined at an angle theta to each other? In that case, the resultant is calculated as r is equal to square root of a squared, that is one of the vectors, plus b squared, the other vector, plus 2ab cos theta. Theta is the angle of inclination as shown in the picture here. And I think at this point it's important for me to mention that the way I've just described calculating resultant velocity for moving in same direction, moving in opposite direction, perpendicular vectors, and inclined vectors, it is not only for velocity. It actually applies to vectors in general, right? When you have vectors moving in the same direction, the resultant is just their sum. Opposite direction, the resultant is their difference. When they are perpendicular, the resultant is square root of the vertical squared plus the horizontal squared, and the direction is as shown here, tan inverse of ay over bx, and when they are inclined, we use this equation shown here. Next, we talk about position. Position is just a point in space. For example, I'm standing at a point right now. This exact point I'm standing is my position. You could be sitting right now to the exact point you are sitting. The exact point you are sitting is your position. A car could be parked outside. That exact point the car is parked is the car's position. So the exact point, a point in space where an object is located is just the object's position. Position is determined by direction and distance from other points. For example, you can describe the position of a car by saying the car is 10 meters to your right. Okay, so you are using your own position to describe the position of the car by stating the distance of the car from where you are and the direction of the car from where you are by saying that the car is 10 meters to your right. So each point has a coordinate of x, y. That is, anytime you talk about position or a point on the coordinate plane, it's always in the form of x, y. For example, on the coordinate plane, you can say a point is located as 3, 5. That 3 represents the x, while the 5 represents the y. That is, the first number represents the x, while the second number represents the y. Distance is the length of space covered by a body as it moves from one point or from one position to another. That is, when a body changes their position and it moves from one position to another position, the amount of space the body covers is distance. For example, if you decide to stand up from where you are right now, you decide to walk 5 meters. That amount of space you cover, that 5 meters, the distance you've covered, the amount of space you've covered is the distance. It is a scalar quantity because distance does not have any sense of direction involved. So distance is scalar quantity and the SI unit of distance is meters. To calculate distance, say distance S is equals to speed times time. So S is equals to speed times time. The distance is the speed multiplied by the time. That is how to calculate distance if you are given the speed and time. But sometimes you'll not be given speed and time. Instead, you know that distance is the amount of space covered when your body moves from one position to another position. So instead of being given speed and time, you may be given the first position, which is x1, y1. You can see you are given a point 1, which is x1, y1, and you are given the second point, which is point 2, as x2, y2. So the distance between point 1 and point 2, in that case, will be calculated as distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared, as written here. Finally, we have displacement. Displacement is distance traveled in a specific direction by a body. So displacement is distance, but displacement has a specific direction. It's just like saying I walk 5 meters to my right. Okay, by saying that I've specified the distance I've walked 5 meters and I've specified the direction to my right. Okay, so displacement is apparently it's a vector quantity because it has direction involved, right? And the SI unit of displacement is meter, just like that of distance. To calculate displacement, we say displacement S is equals to velocity times time. Okay, displacement is velocity multiplied by time because velocity is a vector, right? So displacement is also a vector. So the picture here shows us distance and displacement. Distance is just space, as you can see, it's just a line to represent it, while displacement has a line and an arrow to indicate distance and direction. Thank you very much for listening.